So I'm very happy today to introduce our speaker, an old friend of ours, Lucy Fortson from the University of Minnesota. I think we figured out that you've been more or less around here about 20 years, with big gaps, big intervals in between. Lucy has worked on cosmic ray physics back in the day when we were all at Dead Ray Proving Grounds. But today she's going to be telling us about her more recent career. Lucy got her bachelor's degree at Smith College, then went on to do graduate work at UCLA under the famous or infamous Dave Klein. And went out to your first postdoc at Frascati, working with the famous or infamous Carlo Rubbia.
I really knew how to pick them, right?
I gotta say, yes. And then she went on to a second postdoc at the University of Chicago, working with extremely famous people. We will not mention. And then she went on with a bit of an interesting kink in the usual career to Adler Planetarium, which is a major planetarium, of course, in Chicago, and eventually became vice president for research at the Adler Planetarium, and got in the process obviously interested in public outreach. But she is now a professor of physics and astronomy at the University of Minnesota, where it is getting colder here. And she's also chair of the Citizens Science Alliance, and one of the co-founders of the zoo that she'll be talking about, the zoo with these peculiar animals. So please welcome.
Thank you. Thanks very much, Pierre, and I'm very happy to be here. While at the Adler Planetarium, I was asked as Vice President for Research to come up with a reason why there should be research scientists at a planetarium as opposed to the University of Chicago or Northwestern, so basically to justify my existence. And I basically said, well, those places have one educational model through undergraduates and graduate students, but what we have at the planetarium is the general public. And they said, yeah, so what can they do in research? And I just said, watch. So I got some NSF funding to do a little bit of prototype, and then ran into some folks from Oxford University, and the rest is the Zooniverse. So this is going to be a story about how the Zooniverse was built. So for those of you as instrumentationalists or instrumentation people or whatever, this is basically a story about an instrument and how an instrument was conceived and implemented. And I will also talk about some science along the way that this instrument can do. Okay, so the beginning of the story is with this sort of data deluge that probably many people have heard about. This idea that we have so many sensors, telescopes, earthquake sensors, ocean sensors, smartphones, you name it, sensors everywhere, with just huge amounts of data pouring in without the ability to actually really analyze it. So we have this so-called information explosion, where we have this analysis gap between the volume, the variety, the velocity, and then I always add the fourth V, which is veracity of data, okay? So that's, why you need the analysis. Huh? Yeah, right, exactly. You want that going up too, right? Maybe it's anti-correlated, right? But But the point is, unless you fix this analysis gap, then you're always worried about the veracity of the data. All right, so we've got this information explosion, but the machine algorithms that have been used up to now to analyze the data tend to be only accurate to within 80 to 90%, or they're 80 to 90% efficient. And we can discuss why that is, but for one reason, they tend to use proxies, and I'll come back to that in a second. Okay, so that's one half of the story. And the other half is this, a tiger. All right, so which is better at spotting a tiger in the grass? A computer or a 5-year-old child? Okay, so we can see where this is going, right? So clearly the 5-year-old child with the human brain has been evolutionarily adapted to be really, really good at spotting tigers, okay? Otherwise, she would not be here through her forebears being eaten by tigers or equivalents. Okay, so that's the setup. We've got the machines on the one hand, all right, giving us a lot of data, also working, analyzing all the data too, but we know that to deal with the complexity of some of the images, like a tiger hiding in the bushes, you need a human brain to be able to deal with the image analysis, okay? So the big question is, can humans participate in closing that analysis gap? Okay, so the beginning of the Zooniverse starts with the Galaxy Zoo project. And it's a project that started in 2007 with the Sloan Digital Sky Survey, million galaxies, and the question of whether or not there were any spiral galaxies that were red or any elliptical galaxies that were blue. Spiral galaxies tend to have lots of star formation, so they tend to be blue, whereas elliptical galaxies have, so the theory goes, quenched their star formation and they tend to be red, right? So this is where we get the proxy of the machine coming in. So the Sloan Digital Sky Survey pipeline designers built in a machine proxy whereby they used color, because color is actually, it's a number. You can, instead of identifying the morphology through the complex images, they could say, well, we know 8% of the time a blue galaxy is going to be a disk galaxy and a red galaxy is going to be an elliptical. Okay, so enter Kevin Schwinski from the University of Oxford, a graduate student, who was very interested in star formation in elliptical galaxies. So the machine has just cut out his entire sample, right? So he has to go with the, faced with this prospect of going through a million galaxies and finding a sample of blue ellipticals, if there are any. Okay, so again, it would have been easier had this been, back in the Palomar days, maybe tens of thousands of images. So historically, even professors used to do the analysis by looking at maybe 100 galaxies, that sort of thing. But, really asking a graduate student to go through a million was really not on. Okay, so, that's presaging this slide here. We've got astronomy as the example of this data flood. As I mentioned early on, this is happening in many domains. But this is the Large Synoptic Survey Telescope that's coming up online. And basically it is, 4 orders of magnitude in scale as compared to even the Sloan Digital Sky Survey. So never mind having having as a graduate student go through a Sloan sample. What are you going to do when you've got all these galaxies coming in off of the LSST? All right, so we're back to trying to figure out how to optimize the machine algorithms to do that, because clearly humans aren't going to be able to, fill that entire analysis gap there. Okay, though the question is, and then the rest of the story is all about to what extent can humans actually fill in that analysis gap. Okay, so, right, is the human brain, really morphologically to tell the difference between the different types of galaxies. The human brain cannot be beat. But if you just have one human brain, a poor graduate student who gives up after 50,000, then, you're not doing very well. So what do you need to do? You need to turn that human brain into an algorithm that is computerized, and to do that, you have to crowdsource, right? So along comes the internet, right? Along about the same time as the Sloan Digital Sky Survey, and you end up with the ability given to us through the internet to develop a simple interface that allows the public, the general public, to be able to do a simple morphological classification of galaxies. So Galaxy Zoo was thus launched in 2007 with, again, this very simple interface. You know, is it elliptical or is it spiral? Very simple task, right? So Kevin Schwinski, who was the graduate student, as I mentioned, who did the first 50,000, was, he and his postdoc supervisor, Chris Lintott, set this up. They expected that maybe 20,000 people over a span of 3 years would be able to go through the entire Sloan data set. But in fact, they were very wrong, and very wrong in a good way. So Kevin now has a unit named after him. The Schwinski is the number of galaxies, 50,000 galaxies, that one can actually, physically classify before, handing in your notice to your postdoctoral supervisor. And I should say the design of the website was done at a pub in Oxford when Kevin said to his supervisor, we got to talk about this because I'm not doing this anymore. And so then they thought, well, there's NASA's doing the Stardust at Home project. Maybe if we did something, blah, 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 blah. Okay. And then several beers later, the design on the back of the envelope sort of thing. All right. So here is what happened. The launch occurred, and it was so successul the servers froze at Johns Hopkins. So I'd be talking about Veritas, which I'm doing tomorrow. But anyways, today, because we would have just died had the servers had a technician at Johns Hopkins, which is where the servers were, awake at 2 a.m. in the morning, went in and got a set of new servers up and running, and off we went. All right. So note, classifications per hour, 48 hours into the project. All right. We're already clearing a Schwinski. All right. So it goes on. We had great media coverage. Okay. It didn't hurt that Chris Lintott from Oxford also worked for the BBC. But this is the CNN most popular stories. Scientists seek galaxy hunt help right under man flies to wedding a year early. Fortunately above garlic may cut cow flatulence, and moles good indicator to aging. We assume those are face moles or whatever and not the ones that go underground. Okay, well, we dropped to 3 under. Moles apparently, anything having to do with health rises quite right to the top. But we got beat out by Huge Dog being a reluctant media star, okay? And then my mother held me down again. Fortunately, we were, All right. Anyway, so we got lots of great media coverage. And within 6 months, we were well on our way to actually finishing the entire project, okay? So after cleaning the rock clicks, we had nearly 35 million classifications, okay? Remember, we got a data set of 1 million, okay? So on average, each galaxy was classified 35 times, right? And that equates to 3.3 continuous person years in 6 months' time of effort provided by the volunteers.
So what's a raw click?
I'll get to that. Well, the raw click is, if we go back to the, here, is literally when a person presses a button on the website. That is recorded into a database. And that database is then analyzed afterwards.
That's a one-bit piece of information.
Yep, that's right. That's a piece of information, exactly. And then, there's a lot of interesting things about how you take that information, but that brings me to this plot here. So previously, you had maybe a few experts doing classification of galaxies. You could not assign a probability to whether these experts were right or wrong. When you have 35 people classifying the same galaxy, you can talk about galaxy classification in terms of probabilities. Okay, so here we have on the right-hand side, on the left-hand side, we have a pure elliptical sample. So this plot was selected for spirals. So everything that has, a unit of 1 has the highest probability of being a spiral, right? Therefore, because it's a binary decision, everything that in red here that isn't a spiral should be peaking over here at 0, right? There's a lot of interesting stuff going on. At first, we were unhappy about these events here. After 80, some of the guys in here had 80 classifications, and the public still couldn't decide, right? So clearly, this means that perhaps they're too faint or what have you, but maybe they're just not following the pattern of a classic spiral or elliptical. So it turns out,
Classification is wrong.
yes, but if you've got 40 or 50 people, right, then, you take the average of that, and you can weight, we've done all sorts of interesting studies about how you weight the different users, right, so yes, clearly some of the classifications are going to be wrong, right, but you've got the wisdom of the crowds.
Something in between.
Right, and so it turns out if you look at the ones in the middle, you start to see mergers or other interesting things that are showing up there. Okay, so we've shown that actually humans can help with this analysis gap to some level. So the scale of the problem, all right. We've also shown that you now have the ability to have a measurable accuracy based on this sort of idea of wisdom of the crowds. The question then became with Galaxy Zoo, is it because people like looking at pretty pictures of galaxies, or maybe we can do this with other big data problems, all right, in other fields? So we have to figure out whether we can get the attention of the crowd in general. All right, so just a quick pause here to say that there are other types of citizen science. Many people might be familiar with the Study at Home project. This is a way of engaging people in science, but it's a passive process whereby you download a screensaver and the computer is doing the work for the study project to look for, aliens or what have you.
Destroyed the screen in the process.
Yeah, okay. It's a small price to pay for right. An embittered Study at Home user? But an interesting application of distributed computing nonetheless. Okay, so then there's the data collection style of citizen science. There's all sorts of issues about biases in data collection, which I won't have time to get into, but the Zooniverse exploits the niche of data analysis, again, where it's generally relying on the fact that you have these really complex images that need the human brain to be able to do the classification for. So we need to ask the question, or answer the question, is the crowd interested, and how much time do they have? Okay, is the crowd interested? All right, well, there was a motivation study done on Galaxy Zoo volunteers. 20,000 people contributed to the survey. Okay, for anybody in education research, that's just a huge number. Okay, so the most interesting point that we came out with, it's not because of pretty pictures, it's not because they had an interest in astronomy, although that was, up there. It's because they wanted to contribute to science. At that point, we thought, okay, yeah, good. It's not about the galaxies. We can put any science project up here, and we'll have a good fraction of the people interested in doing this. The next question was, all right, we had a couple 100,000 people with Galaxy Zoo. Is that all? that we're going to get out of the 7 billion people on the planet? Well, let's look at how much attention they have. Okay, so this is the box that represents the number of U.S. adults watching TV, which is 200 billion hours a year. Okay. Compared to the 100 million hours to create Wikipedia. Okay. Wait for it. But 16 years, every day, playing Angry Birds. And of course, my son says I have to update the slide because Angry Birds, who does that anymore, right? So anyways, clearly there is a cognitive surplus out there, all right? We can tap into that. Okay, so we did, and we built the Zooniverse. Don't ask about the name. Here we are. It's called the Zooniverse. It's Citizen Science Portal. We have about 1.5 million volunteers around the world, basically contributing to real research. It is definitely a solution to this big data problem. We have found through a very deliberate set of tests and which types of data the public will look at. Images, simulations, text, videos, sound clips, they'll absorb it all. We've got 50 projects and growing across a wide range of topics and over 100 peer-reviewed publications, including several discoveries made by the members of the public, which I'll point out. I'll spend a little bit more time on that. We are hosted by Amazon Web Services, which allows us to scale. For example, when Chris Lintott goes on one of the big stargazing live programs over there in the UK, we can have within minutes hundreds of thousands of users sign on to a project. All right, so we need to have that scaling ability. Our funding is primarily by the National Science Foundation, Sloan Foundation, Google, the Leverhulme Trust in the UK, and as Pierre mentioned at the beginning, we're operated by the Citizen Science Alliance, and the member institutions are listed here. Okay, so from galaxies to ancient papyri fragments, it's really the same thing. You just have to look at the image and compare the letter, it's in Greek, to the keyboard, and take your best shot at matching the letter on the keyboard to the letter on the fragment. And in this manner, we have found poems by Simone in fragments of papyri, and a whole suite of things that have come out of the desert. And this, by the way, was from a garbage dump. The whole Oxyrhynchus collection was a garbage dump from the Oxyrhynchus town in Egypt. Then bringing it home, thanks to Anil, we have the Andromeda Project, which was a collaboration between Utah, Minnesota, and the University of Washington to look for star clusters in the HST fields of the M31 Andromeda. And, we'll get to a little bit more about the Andromeda story a bit later, but basically it is still the most rocking project we've ever had. Okay, so it sets a bar for us. And then moving into ecology, we have Snapshot Serengeti, which is basically setting up a bunch of camera traps. It turns out that elephants don't like camera traps. So every time they see a camera trap, I guess it's the little red light that's blinking that it's on, makes the elephants charge at it. And, well, yeah, this is what happens afterwards. Okay. And then you get, other inquisitive animals going, what is that? And the point of it, though, is for studying the predator-prey relationship in the Serengeti and looking in principle at lions, which in the past, before camera traps, had radio collars, which is a very invasive way of tracing their movements throughout the park. And
The problem of invasion of privacy?
Oh, yeah. Well, we have a chimp project now, and they do very interesting things. Some of the animals in Snapshot Serengeti do very interesting things. On both sides of the spectrum, they're having lunch on other animals as well as creating more animals. So you can find some stuff there. We also have, it's hard to see, but we can classify in this filtering method by rump style. So, because a lot of times they show their butts to us. And butts are a really good way of differentiating between species. Okay, so the point of this all then is instead of radio collaring lions, you get the full swath of all the species that are out there in the Serengeti, which allows you to monitor migration patterns and do a whole bunch of really great ecological science out there.
What's the density of those cameras?
It's 250 cameras in I don't remember off the top of my head what the area of the Serengeti National Park is. Sorry.
Okay. That works.
And so for each Zooniverse project, we have found by sometimes bitter experience that what you need is a talk discussion board, so a forum, because when a person comes to the site, you need to be able to give them feedback right away. You can't just have them clicking, and a lot of times there's this threshold fear people have, and they start on a project, they think it's really hard, and they're worried that the data that they're contributing is going to mess everything up. But you have to get them over that. And it's like, no. It doesn't matter if you screw every single one of your classifications up. It doesn't matter. So it's the wisdom of the crowd. So it's going towards the mean. So you need to be able to have the talk for other reasons as well, which I'll get into, which is a mechanism for the public to make discoveries. You need a way to communicate to them other than through the talk, but keeping them informed of, for example, the discoveries that are made or the papers that you're publishing, or et cetera. And then there are a whole bunch of other mechanisms, social media mechanisms that I don't know all that much about. I tweet, but that's about it. I don't do Snapchat or any of that stuff. The point is that we found that an engaged science team is absolutely essential for project success. And that means when you launch, you're there 24/7. I don't know, you guys were on, 24/7 helping people through the Andromeda project. So this is the growth of the Zooniverse over time, since 2007 when we launched, and all the way up to, this is actually 2012, I think. So I forgot to replace the slide. But the bottom line is we've reached a point in our growth curve where word of mouth actually matters now. We have enough people that if you launch a project, in fact, actually, I think Andromeda was one of the first ones that set the stage for this, where there really wasn't actually that much media attention at the beginning. So it was really through word of mouth that people found the Andromeda project and then destroyed all the records.
Some of the events that cause these jumps?
Okay, yes. So these are, for example, media spikes. So it's a project launch. So each of these, you can't read it from there. Each of these spikes is a new project, right? So you launch a new project, you focus a lot of attention on that, and then, you raise the level. They stick around. Some fraction of them will stick around, and they'll try other projects. Okay. And so we use Google Analytics to monitor everything. I don't want to go through this too much. I have a more in-depth version of this slide, but the bottom line is, number of visitors versus amount of time they spend on the site, and the size of the project is related to the number of classifications. And we can divide it up into how many people are doing what on the different projects, which we can see here. So just in the last year alone, we had 108 FTE equivalent, full-time equivalents across all Zooniverse projects. And, we had chimpanzee, you get it? Chimpanzee, right? Takes a lot of people a long time to get that one. Anyways, so you can see in chimpanzee that, it's a fairly popular project. Penguin watch. Oh my goodness, people love to count penguins. Almost up there with galaxies, okay? So, yeah, our animal ones are really, really popular. So, okay, so we have, this is a recent paper, Cox et al. 2015, where they have created this so-called success matrix, where you have the amount of public engagement, which is measured by, sort of 6 metrics, that, is like numbers of posts on the talk forum and this sort of thing, versus contribution to science, which is sort of some of the obvious things like, how many papers has the project published, that sort of thing, right? There is no absolute scale to this. So these are not failures over here. These just are slightly slower in their classifications, okay? Galaxy Zoo has, I forget, we have like 40 papers now based on data from, and okay, yes, it is, before anybody asks, it is not scaled to time time since project launch. Okay, so but it is interesting to see how they distribute, and yes, you can look and see, for example, some of these did not have a very engaged science team. Some of them had a very engaged science team, Cyclone Center, but it was too hard. Okay, so here's the Andromeda Project. Nothing has beat that yet. And in fact, it's moved over here because you guys have a publication. Yeah. So I don't know what we're going to do. Think of another project, right? Yeah. So Andromeda Project is just off the charts. Okay, so this is why it doesn't matter if your classifications are wrong necessarily. Right? So this represents all of the volunteer contributions to a project which we call Old Weather, which is basically a climate change project which gets people to do transcriptions of weather logs from World War I on the UK ships that were traveling around the surface of the oceans during World War I. And each box represents the number of transcriptions for a single user. Right? So we got our power users up here, and we got the people way down here like, what's this thing? I don't know, some of my cousin told me about this project. Nah. Okay. Right? So if you think about it, the entire area is the integrated number of classifications. If you split it in half, right? Half of the classifications are done by people who don't stick around all that long. The other half done by people who become our moderators and very engaged in the project, and trickle down to the extent that they are pulling more people from this side over to this side through their engagement in it. Right? But the key message that I wanted to take away from this is it takes multiple independent classifications to fully creates the strength of this human computation aspect. So there are other projects which, like protein folding projects like Foldit, which use gamification as a way to incentivize people to participate. We have decided we don't use gamification because we wouldn't have multiple independent classifiers. We would have people who would leave the system. We've done the study, actually. Leave the system because they don't like the competition factor. But Foldit takes the attitude. The structure of their citizen science project is they are looking for the one person who is actually able to fold a protein in the minimal energy state, into the minimal energy state. So they're looking for a very specific skill. And gamification is the one way to do that. right? So we don't gamify. We want everybody. All right, so we have constructed a set of ethics. There must be a legitimate science topic which has publication potential. We will not accept a project that does not have publication as a potential. If the machines can do it already, not a Zooniverse project. It would be wasting our volunteers' time. And you have to keep the volunteers informed of the progress because they are your workhorse. They are giving you the data, and they need the encouragement. Okay, so this is just a cartoon of how the Zooniverse works. We have a classification interface for a given project. You have a visitor pounding away at their interface. The data goes to a classification processor, decides if the subject that we call these images subjects is going to get retired, meaning taken out of the system, and then selects the next subject to show into the classification interface, and then the loop goes. There's also this consensus engine, which is at this point on the back end and looks at this classification processor to tell you when you've gotten to a point, which I should actually have another arrow here that actually goes to the retirement system as well now. This used to be, we would only give the consensus at the end to the scientists.
I'm worried about the retirement system. Are you able to cancel people out of this without their permission?
No, it's not retiring a person.
Oh.
I have a really bad joke to say, but I'm not going to say it. Thank you, Pierre. Okay, so sorry. So this is all great. So we've got 50 projects up and running, but we've had 15 developers. A lot of money, 15 developers. We're the bottleneck. We get hundreds of legitimate proposals a year to do a Zooniverse project. We are the bottleneck. So a couple years ago, we got funded to write a do-it-yourself Zooniverse project builder so that anybody who wants to build a Zooniverse project can literally do this now in 30 minutes. Well, okay, maybe 2 hours. But like if you've ever put a blog together with WordPress, it's about as easy as doing that, right? So you need an image set, and you need to write out your workflow, and then you can put your workflow, in the format, upload your images, and bada boom, you've got a Zooniverse project. This one was one of our first using the project builder, Fossil Finder. This is basically looking at images from drones that are flying over Lake Turkana, Kenya, looking for fossils in the images, and these are all geo-stamped so that the ground crew, when they get information from the citizen scientists that they've found a fossil, they will drive out to that particular site and collect the fossils. Right? And within 6 weeks of running, they found a set of fossils that are, I can't remember what kind of fossils they are. Human? I'll just say human because that's, dramatic impact there. Okay. All right, so there are 3 ways to use the project builder. The other thing that we were getting requests for was, well, medical science, yeah, okay, but where's your IRB? No, we can't have this public. Are you kidding me? This is somebody's tissue data that they don't want the entire public to be seeing, or some other kind of sensitive projects. So we now have the ability with the project builder, so you can host a project on your own behind a firewall, right? You can certainly make it a public project, and if it passes internal peer review, we'll post it on the Zooniverse and host it. And then you can also do custom designs. The code is all on GitHub. And we have found since July, more than 700 people or teams have created their own project using the project builder. Many of them aren't all that great, but but many of them are. And we've got, we've got about 10 projects that are currently cycling through the review stage. Okay, so what else can we do with the attention of the crowd? We can do serendipitous discoveries. So this is where the forums or the talk comes in very handy. We've got this thing called a green pea, which turns out to be a new kind of galaxy that Hanny Van Arkel discovered through just this little cute post, give peas a chance. And this evolved into other people on the forum posting their peas and creating the peas core and, all sorts of fun jokes. But they ended up doing very serious science. It turns out that the astronomers weren't paying attention to these guys, and there were about 20 of them that were working together to identify and literally set out criteria for what a pea galaxy was.
Are those things really green colored?
Yes, I'll show you why in a second. Well, depends on. Color is subjective at some level, but I'll show you why they show up as green. So here we have on the interface we had this galaxy reference number here, which basically you could click and you could get to the Sloan Digital Sky Survey information page about the galaxy. Okay, so here, this is the reason why it's green. So this is this humongous O3 line here, which is an indication of very high amounts of star formation, and it the wavelength of 5,007 angstroms is 5,007 angstroms, sits right in the green filter for the Sloan. So it literally saturates the Sloan green filter. That's why it shows up as green. So these astute volunteers noticed that this thing did not look at all like a normal galaxy spectrum. They didn't know what a spectrum was, but they could, they're pattern matching, right? They could tell that this was very, very different. So that became one of the criteria for the search of the piece. All right, so in the end, they discovered about 250. They ended up writing a computer algorithm to go in based on these classifications, their set of criteria, and writing a computer algorithm to go in and search the Sloan. And this has become a veritable cottage industry, even up to today, where these are potentially, very compact but very high star formation rate galaxies that could end up being what these so-called Lyman continuum leakage galaxies are, which has a lot of potential impact on galaxy evolution and some of those questions. So the other project that we've had lots of interaction with from the public is the Planet Hunters, and this is just, the interface that we use here. We were scared to death of putting this one out because, oh my God, it's real data. And the public would go running because it's real data, but no, they eat this one up, okay? So it's looking for dips in the starlight with presumably a planet going in front of the star causing the dip, okay? Fairly straightforward. So this is the consensus. The purple is basically where the most number of people have found the dip. And then again, we find that there are people who, again, this cognitive surplus. Instead of watching TV, they're creating Excel spreadsheets to do the transit folding in Excel. To accentuate the transits, and then ending up, okay, so they zoom out, and yes, it has the shape of a planet transit, and then educating everybody else by showing the code that they're using and how to do this, and discovering a planet. All right, so this is Planet Hunters 1, discovered a couple years ago, made it to CNN. This, of course, is an artist's interpretation from the planet. But it is the first planet to be discovered around a double star system. All right, so I don't know how Newtonian mechanics works really on that. But I don't know if you've heard about that alien structure around a star that's been in the news lately. Well, that was another Planet Hunters discovery, all right? So the thing to note here, so this is the transit pattern. Generally speaking, for a planet, a transit, it's only a fraction of a % of the light dip. This is, a huge percentage of the light dip for a given star, and it's not periodic. Okay, so the question is it one of these Dyson spheres of a structure around? Okay, well, that'd be cool, but probably not. But the theory that the explanation that the science team has come up with is it could be a cometary system that's being pulled apart, a very large comet that's being pulled apart and creating this sort of stochastic light curve. But I also want to point out that this is the discovery paper. Take a look at the list of authors here, right? Okay, notice all those institutions? It's pretty up there institutions, right? Second author, the guy who discovered it, right? Right. We are really changing the game here, seriously, right? We are having a huge impact on having amateur astronomers being recognized for the work that they are doing. And that is clearly, that can motivate a lot of people to do things. And here's our old friend. So, his wisdom. Oh, his wisdom. It's true, though, right? This is an amazing statement that he made, right? So we have the known knowns. I'm sure that, I think this is, probably a Chinese proverb or something like that. But, all right, known knowns, primary task, build a task. This is what we want people to do. Known unknowns. Well, I didn't show you this, but this is Hanny's Vorwerp. It's a strange system that it's basically the death of a quasar. Just let's leave it at that. Theorized to exist, but never having been seen before until Galaxy Zoo. Then we've got things like that are the serendipitous discoveries that people didn't know about at all. It's the unknown unknowns. Okay, so the question is, how can we build a system that takes advantage of all of these three types of knowledge discovery? And I'll just flip through that. I gave the education talk this morning. So machine learning. And so I'll finish off with a whole discussion about machine learning and where we're going, making a partnership between humans and machines to get the best out of what machines can do and what humans can do. Okay, so the simple-minded version of this is we've got this big data flood coming in. We have the machine classifications. The machine classifications are only 80% good. Hand them off to the citizen scientists. Citizen scientists go classifying away. They create a set of classifications that can get passed back to improving the machines with better training data. Okay, so that's the simple-minded loop there. But we're going to do better than that, right? But in order to understand how to do better than that, to have them working in parallel together, we have to first at least implement this loop, which is what we've done in real time with Supernova Zoo. This was done in 2012, or actually 2011, where we had the Palomar Transient Factory was getting information off the skies that potentially were supernova candidates. And the issue is it's very expensive to go follow up on a supernova candidate. So you want to be darn sure that you've got a really good supernova candidate. The machine algorithms were sending too much garbage to the follow-ups. So get the humans in the loop, and that can be improved. It also, this whole loop, enables social system research to be able to optimize the human attention, and I'll get into that in a second. But picking up for the Supernova Zoo, so we have a potential candidate here. The research team could view, basically the way it worked is, as the humans were doing the classification, the probability, you created a table that was based on the probability of the candidate actually being a good candidate, and then you could pick off from the top of the table the ones that you would send to the follow-up. And, there were ATELs that were sent out, and, of course, it was great to publicity that we were in the discovery. And this is where it gets kind of interesting. So this is a movie. And this is some of the social systems research that we're doing, because what we can do is we can track and build a model of accuracy for each classifier. Each person that is submitting classifications. And the movie's not going to work. Oh, come on. Really? No, I tested it before. It didn't work. No. Okay. That's all right. We'll go to the next slide. So this is just basically a chart which shows this is the real not a supernova. This is, the blue line is if it's really not a supernova. The red line is if it really is a supernova. And the corners, the apexes of the triangles are basically, this is if the person votes that it's a supernova, if they vote that it's not a supernova. Sorry. If it is a supernova, not quite sure, and definitely not a supernova. So you can track the accuracy over time. So this is their learning phase, right? And so, this person starts getting better at being able to identify supernovas, right? You can see the trajectory of the red line getting closer to the, oh no, sorry, I've got that backwards. This guy is actually not very good. But so the bottom line is you can really track. Each user has a very different signature, right? And so what you want to do is you want to be able to use this information to send to each user the thing that they are good at. Okay, so maybe you don't want to send this is maybe where you retire people off the system, right? Okay, one of the other things that we've done is this is with the Space Warps project, looking for gravitationally lensed systems, as we inject simulated events, right? Gold standard simulated events that then basically trains up the humans. But at the same time, it allows us to have an absolute measure of the accuracy of the humans as they go. And then what that allows us to do is to create a dynamic retirement system. And this is somewhat complex, so bear with me for a second. I know I'm nearly done. This here is a plot of the probability of a particular object being a lens, right? And this is the number of classifications. So you start with a set of priors. So each subject, as it starts here at the top, there's no classifications up here, right? It starts with 0 classifications, right? So it comes in, and each time it gets classified is marked by one of the dots here, black dots. So each time it's like a pinball machine. Think about it that way, cascading through. So each time it gets classified by a different agent, it pings back and forth as it goes down, right? Because one guy says it is, one guy says it isn't, right? So it goes do, 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 do. But as the wisdom of the crowd works, if it crosses, it's probably very hard for you to see down here, but there is a line here which is set as the detection threshold at 0.95, right? So once it crosses that line, then it is retired from the system. As it ping-pongs its way through to the rejection threshold, then it's retired. And you can see that it takes about 10 classifications on average for a subject to get retired. So this is done dynamically, and not only that, you can, again, you can use the information. So when it crosses this threshold, the system says, okay, I now have a candidate for retirement. I am now going to use my accuracy profiles of my humans and serve it to 3 experts to make sure the machine isn't going to make a mistake. Okay? So it's crossed this threshold, but it could be wrong, right? So let me serve it to 3 known experts that I've drawn from a pool of experts because I know what their profile is, right? So this is done currently every 24 hours. We rerun the system and retire subjects out and then create the next set of subjects for people to classify. And this is the confusion matrix, which I won't take time to go through. Okay. This is, I was kind of two minds to use this, but all right. Really what we're going for is the symbiotic nature of, humans and machines working together. So what we need is an algorithm or a set of algorithms that are capable of classifying this huge amount of data that's going to be coming from the LSST. And that algorithm has to be smart enough to know what to send to the humans for either verification or classification. This whole idea of citizen science and the humans being able to close that analysis gap, well, we tested that out with Galaxy Zoo. And we found, yes, indeed, the humans can help close that analysis gap. But that was only on the sort of scale of the current amount of data flooding in. When the LSST comes online and its equivalents in other domains, the relationship has to change, okay? We have to improve these algorithms by jointly sharing responsibility between the machines and the humans. What we're working on right now is, this is supposed to mean the research teams. Okay. The LSST data comes into the hallowed halls of academia, and then, it passes back and forth between the Zooniverse. The Zooniverse passes to the public. So that's the kind of mode that we have right now. All right, so these guys talk back and forth between the research teams. And now we're putting the machines into the loop as well. So this is kind of where we are, but where we want to be is, again, using this combined process of humans and machines, and then, of course, acknowledging the amateurs along the way as part of academia. One example of a project that we're using this on is an advanced LIGO project, which we're calling Glitch Detective. And the bottom line is, LIGO, which is a gravitational wave detector, several of them, one in Louisiana, one in Washington State, and one in India are going to come online. The point is that you're basically looking for a change in the position of a mirror. Let's just leave it at that. On the scale of a fraction of a nucleus. So you're really looking for that level of accuracy in your system. So there's 10,000 monitors set up because, for example, in the Hanford, Washington LIGO site, the Columbia River is very close by, and there's a dam. When they open the dam, that shows up in the system, all right, as not quite a glitch, it's a little bit more of a glotch, but but you've got things that might be, glitches, like somebody closes the door too hard, whatever, okay? A car goes by. So there are hundreds, tens to hundreds of glitches seen by LIGO a day. And a few of them are known, but not all of them. And so many of these glitches fall into categories that are in the unknown categories. Some of them are in the known unknowns, and then you just need to train your computer algorithms better. So I'm not going to walk through this whole thing, but the bottom line is this Advanced LIGO Glitch Zoo is one of the first opportunities we have to really test this human-machine partnership together. And so with that, I want to thank you. You're supposed to do faster than that. Okay, thank you. Thank you from the Zooniverse. And I'll leave you with one of my favorite slides, which is this is a cheetah seen in Snapshot Serengeti, and then all of the pixels are made up of galaxies from Galaxy Zoo. So,
Questions?
Don't you have historical pictures of supernovae that would be used for training?
yeah.
This is what it looks like when it begins.
Absolutely.
So
Absolutely, right. And in fact, the Harvard Observatory has a project, not a Zooniverse project, but they have a project that they are working on to
train
use.
observers.
Yeah, yeah. Everybody wants to go. Question.
So I was just wondering whether you could use this project to distinguish quasars and galaxies in the next SDSS survey, which is SDSS 4. Is that possible? I understand that that's something of a problem because the galaxies are pretty, those images are pretty faint.
Yeah, the difficult. Yeah, I mean, the humans have their limits,
Yeah.
right? But this is where the combination of humans and machines, we hope, can tackle problems like that. So it can be that the humans over a long period of time can get better with these really faint images. I mean, Galaxy Zoo 4 has done Hubble, has like the Cosmos surveys, and and we're finding it's really, really hard to debias the catalog. We're in my team at the University of Minnesota is in the process of building the Hubble catalog of classified galaxies. It's really hard for the public to go down to certain magnitudes. But even data that they don't do well at, there's information there. And that information can then be used to help the machines a little bit better.
Do you guys have competition? Is there a Zooniverse competitor that is? I'm just curious.
Like in what sense? And
I mean, like you're doing specifically data analysis,
Uh-huh.
kind of citizen science. Is there another large organization?
Oh, are the competitors to Zooniverse? Nobody can ever get down. Well, yes, actually, there are a few. I'm not going to give you their names, because I can't remember them. Yeah, it was a matter of timing. I mean, we were there right when this all took off. It was a sort of a perfect, not storm, but yeah. So we more or less dominated the data analysis side. Yeah. Yeah.
So I've thought about these kinds of applications in terms of how you might do this within astronomical spectroscopy. And in particular, one of the problems that comes up in my mind is that the thing you want to be looking at is a spectrum that's already been subject to a fairly substantial amount of calibration and processing to get down to what you're actually looking at. And that whole processing chain is something that's evolving over time, and the quality is, we hope, improving. So you might have a campaign to classify a whole bunch of galaxies, but then, say, a year or 2 or 3 years later, you might want to do it all again. Because
Exactly.
your reductions are better. Is that something that you could realistically sustain within this kind of framework, or do people get bored and they want to move on to...
No. I mean, we've done Galaxy Zoo reprocessing multiple times. The Sloan data has gone through. We've done Stripe 82 several times, for example. We've done there are certain subsets for a variety of reasons that we put in. Again, you always tell them. You're absolutely forthright with the users on what you're doing. You're saying we are putting back in, the original Sloan survey because, and they'll, for that type of purpose, it's completely legitimate. Yep.
Is that what the Galaxy Zoo 1, 2, and 3 was?
And 4, yeah, right.
Okay.
Yeah, right. We're now on illustrious simulations. So we're actually doing simulated. Yeah.
Okay.
Yeah. Yes, that's right. Sorry. Thank you. Right. I misunderstood your question. Yeah, different data sets. So two was a reformulation of the task for the Sloan Digital Sky Survey. 3 was the Hubble sequence. I've lost track of what 4 was. 4 was UKIDS, and I don't remember. Anyways, yeah.
So I have a question.
Sure, yeah.
So you're using this cognitive surplus. This is just clearly a major force in people's desires to do things. The other major force is greed. Do you think I'm combining this and turning into a gambling situation? You could be making lots of money.
I thought it was in Utah, not Nevada. Yeah, I know, just, past Dugway, right?
Scalping is legal here, remember that.
It's, well, okay, so we did a Kickstarter funding round for Snapshot Serengeti, and we actually got some negative feedback, even just having, I mean, this isn't winning money, I get it, right? But it's giving money, so yes, right. But yeah, but no, I
It's a purity factor here.
well, okay, so in all seriousness, Amazon Mechanical Turk is a crowdsourcing platform run by Amazon, which pays by the bit, right? And it's, don't go thinking you're going to make lots of money by doing this stuff on Amazon Mechanical Turk, because it's like, a quarter of a penny for a classification or something like that. But I mean, there's a lot of ethical issues around that. And furthermore, we have lots. We work with Microsoft Research and Google Research, and we have all these teams that are using our data to look at things because we aren't tainted, we aren't biased by the incentives that money then put forth.
So is the NSA interested in your
Oh yeah,
processor?
that's all I can say.
So,
Our trip to Utah was funded for other reasons.
For all of you, yeah, I mean, face.
I mean, you talk about big data. Where is it? Right down the road.
Yeah.
So let's thank the speaker one more time.